So recently, Alibaba released a paper titled AlphaMath that integrates planning with large language models to enhance mathematical reasoning abilities of large language models like ChatGPT or Llama 3. So today we are going to look at that paper. So let's get started. So the title of the paper is AlphaMath Almost Zero because it is motivated by AlphaGo system of DeepMind. So let's see what exactly they are targeting. So they are targeting to improve the mathematical reasoning abilities of large language models like Llama 3 and ChatGPT. And how do they go about it? They combine POT or /PAL, which stands for program of thought, and program aided language style of approach, which is similar to chain of thought thinking, and add Monte Carlo Tree Search on top of it. This is further combined with a symbolic system like a Python interpreter, and eventually their system leads to better mathematical abilities. Now we are going to deep dive into what exactly they are trying to do. So the premise of the work is that current large language models struggle to do complex tasks that require multiple sequence of steps to reach a conclusion, right? For example, if you give it a mathematical problem that will require a sequence of steps for derivation, it will usually fail to do that, right? And a solution to that would be to create a data store where the data contains a query and a sequence of steps, right? These steps are then used to fine tune a particular model that is pre-trained, right? But the problem with this approach is that you have to create this data set first, right? And this will require expert annotators, which are very rare to find. For example, if you want to solve a derivation of mathematical problem, then you cannot randomly ask a normal human being to do that, to annotate. For example, that is not the case for annotation of images, like whether it is a cat or dog, etc. But so this problem is very specific to solving reasoning tasks because the annotator has to be an expert in this case. So what is the solution to this? So these people highlighted some of the methods here that say that, okay, for example, the method number 19 and 43, you can check out the paper, use both human annotation as well as annotation from GPT-4. Whereas methods 12, 23 and 35 use only GPT-4, and their method essentially uses neither of these. They use something called planning that allows them to not have a data set of this, right? And the motivation for that is that humans do not do that. Humans, while they have some form of supervision with them, they still have a way to backtrack their thinking if they have reached a particular conclusion that is contradictory to what they believe. For example, if you are doing a derivation of a mathematical formulation, right, and you reach a conclusion that says that 1 is equal to 0, then you know that somewhere you went wrong. So you can always go backtrack and see where exactly you went wrong and continue the derivation from there, right? So this is the intention of this paper, that can we do that. So for this, before we jump into the actual approach, let's see what is program of thought and program aided language. These are two papers that were published recently. So what they do is that they ask large language model to write program of its thoughts and processes, and then program is then executed using an external interpreter like Python and all. So it will ask that what are you thinking, write a Python code for that. Then it will use a Python interpreter to execute and return the intermediary result, and that intermediary result is then used to formulate the answer. Okay. For example, if you ask, this is an example given in the POT paper, that is program of thought paper. It says that, let's say you want to ask the large language model that you give it a query that what is the 10th Fibonacci number, where the first Fibonacci number is 0, second is 1, and the next number in the Fibonacci series is the sum of the two numbers, right? So it will come out to be 1, then 2, then 3, and so on and so forth. So if you give this prompt to large language models, they usually, what they do is that if you ask it what is the 100th number, it will usually end up giving a very incorrect answer, right? But if you ask, for example, in the paper program of thought, what they did is they asked it to write a code for that. That means they want it to think in the terms of programs, and when you execute that program, it will return the final answer. And in that case, they showed in their paper that this led to better results overall, right? Okay, so this is what they want to do. So this is a 3-step process. They will first create a data store for this. Then they will use something called Monte Carlo Tree Search. If you are not familiar with Monte Carlo Tree Search, it is a planning approach, very old planning approach. We have discussed this in previous couple of videos. I will leave a link in the description. And then they will create a data store using this MCTS to train the final large language model, right? But how do they do it? That is where the innovation lies. Okay, so these are the three steps they have written. The first, we collect a mathematical data set that comprises pairs of question and their corresponding answers, and this is the reason the title of the paper is AlphaMath Almost Zero, not exactly AlphaMath Zero, because they start with a data set, right? And that is not the case with AlphaGo Zero. And then they employ MCTS, which is Monte Carlo Tree Search, for planning based algorithm, and they finally use this to train or fine tune, or at the inference time they optimize the policy, and then at the inference time they simply leverage this large language model. Okay, so let's go to the next part of this now. So let's see how exactly they employ their Monte Carlo Tree Search. Because Monte Carlo Tree Search is a planning based solution, that means it will require you to define an Markov decision process, right? So you need three things to define that. You will need state, you will need actions, you will need the reward functions. And because it's a deterministic process, you will you do not need to define the transition function, because you simply concatenate whatever you are generating so far. Okay, so for state, what they say is that whatever is the partially generated solution so far, you label it as the state. Action is the next set of tokens that you can add, and reward function will come to that. Transition function, that means what should be the next state given the current state and the current action. You simply concatenate the current partially generated code and the token that you selected. You simply concatenate, this is the concatenation operator, and that becomes your next state, right? So now let's see how they define the reward function. So what they say is that because it's a program generation, if you execute that program at the end and it gives you a correct final answer, then the reward is +1. If it gives incorrect final answer, the reward is -1. Otherwise, in all the intermediate states, it will always be 0. That means if you have generated a partial code so far, then it will return a reward of 0. So there is a reward associated only when you are satisfied that the code is complete, whether it is incorrect or correct, right? That is separate. Okay, so they say that given any input question, the solution process can be broken down into multiple reasoning steps. This is the very first assumption. This is what the task was all about, right? So they say that we will grow a Monte Carlo tree to search for an optimal solution for this, where the policy is given by the large language model associated that you want to fine tune. The next state is simply the concatenation of the current state and the token that you picked, right? Okay, so how do they go about applying a particular Monte Carlo tree search? So we saw what was the primary goal. The primary goal was to develop step level value model, right? So that if you have a partially generated sequence of tokens, that means partially generated code, how good is that code? That is the function they want to learn. So that means they want to learn the value function of the state, where the state is the partially generated code so far, right? This value function, that means what is the value of the partially generated code, that implies what is the expected return of that code. That means what is, in general, you can think of it like, what is the chance that this partially generated code is eventually going to lead to a successful completion. For example, let's say you have partially generated a code of int a multiplied by 3 and then you have added semicolon. So this is the value of this particular partially generated code. Let's say s is equal to s1 is equal to this, should be very low, because this is an incorrect sequence of tokens that you have attached. Whereas in the case where you have another sequence of tokens, int a is equal to, let's say, 10, right, then the value of this s2 should ideally be, we would like it to be greater than value of s1, because this is a correct code and this will definitely lead to a bad execution, right? So this is the primary goal, and their reward function we have already discussed. And what is the value of a particular state? An optimal value would be, it would be that given a partial solution to you, that means ST, you execute, right, a set of actions, you append a sequence of tokens that is usually called as rollout in the case of reinforcement learning, right, and you execute it till the end, and then you take an average of number of such executions, a number of such rollouts that you have done. So this is the you can say, you can usually, it is called as Monte Carlo evaluation. So what is happening, why it is called Monte Carlo? Because you are sampling it, you are sampling all the possible sequence of tokens that can happen given a partial program ST. And why is it called evaluation? Because you are evaluating the value of a particular partial solution ST, right? Okay. So now once you have what should be the value, this becomes very easy for us. Can we target this particular, right, this particular function in the loss as a loss function, as a part of the loss function, right? So if we parameterize our value function using 5 parameters, a network 5, a set of parameters 5 of a network, where the target is the value coming from the Monte Carlo evaluation, then this becomes our loss function, right? Okay. So now let's see, after this preliminaries, let's see how they apply Monte Carlo tree search on top of it, right? So Monte Carlo tree search, briefly to say, it consists of 4 steps. Step 1 is selection, second is expansion, third is evaluation, fourth is backup. In the selection phase, you select a particular node in the already existing Monte Carlo tree that needs to be expanded next. Once the particular node is selected, in the second step you expand it. Then once it is expanded, because it's still a partially generated code, you have to evaluate it, because it cannot be evaluated as it is. It will throw you a like syntax error, right? Code any other form of code compilation error, or it may be a complete piece of code in itself, but it may not lead to the desired result, right? So you evaluate it. The fourth step is backup. That means you back up the value that you have estimated for the node that was expanded in the second step and was selected in the first step. Okay, so that's what they have done. So at each step, what you will do is that you will select a node, expand it, evaluate it, and backup it. So that is called the ith simulation of MCTS. So in every ith simulation, you have to select which node. First step would be to select which node to expand. For that, they use a famous algorithm called PUCT algorithm. Here it strikes the balance between a couple of things. Let's go through these things one by one. First thing is, what is the estimated value of taking a particular action given a particular state. That means, let's say if your partial solution ST is equal to int a is equal to 3 and your next action is equal to semicolon, then what is the value of taking this particular action in this particular state? That is given by QSTA. Okay, so second term that they are balancing or they are using to define which action to take is what does the policy think? That means you have an LLM, right? So it is a language model. So that means it has a probability distribution over all the actions that you can take. So what is the probability that the LLM thinks that you will use a semicolon, right? That is being multiplied by two things here. One is the numerator and one is the denominator. Let's go through them one by one. The numerator says that how many times in the tree have you visited the parent of this action A, right? And the denominator says how many times have you visited this particular action given the particular state. So essentially what you are saying is that given a tree like this, right, let's say this is int a is equal to 3 and this is the semicolon and this is, let's say, a comma, right? So now how many times have you actually reached at this state divided by how many times have you picked this semicolon rather than the other actions, right? So how does it matter? How does it affect the particular value? How does it balance the exploration versus exploitation trade-off? It balances it in a way that if you have visited your parent very often, that means the value is, this particular value is very high, but you have never visited this particular action, that means this particular value is very low, that means this overall number will be high because you are dividing a large number by a smaller number. So that means that this positive value, this particular positive value will get added to another, the q value, and hence shifting it upwards, right? Now let's say it is the other way around. That means the numerator is low and the denominator is high. Is this possible? No, it is not possible, because you have to visit the parent in order to visit the in order to visit the action, right? So that means that if you have visited your parent, very often, and you have picked this action also very often, that means you should, these two values will be very close to each other, so this will turn out to be roughly equal to 1, let's say. So that means that for other actions, this particular ratio will be very low for other actions, right? So in this case you will prefer taking the other action, so that means you are exploring more often. So that is the balance you can have for PUCT algorithm, right? So this is how you balance out which action to try out next. Okay, once you have decided which action to try out next or which node to expand next, you simply expand this, right? Right, so you simply expand this particular node. Let's say you decided to expand this this particular node, then what you do is that you add all the action possible for this particular state. Okay, once you have expanded, the third step is to evaluate. And how do you evaluate? Because this particular program, whatever you have picked, may or may not be a, this particular program that you have picked may or may not be a complete program, or it may be a complete program but it may not still lead you to a the desired result, or it is targeting a desired result. For example, int a is equal to 3 semicolon itself is a complete program, but it is not a program that it gives you the desired result. So the reward in this case should be -1, right? So what you do is, let's say this is a partial solution. What you will do in the case of evaluation is that you will generate all the next possible values, next possible tokens till the end of the program, and then execute it to get whether you get a positive reward or a negative reward. Based on whether you got a positive reward or negative reward, you will update the values that lie in the path of this particular node from the root. That means you will update this particular branch, right? And you will not touch the value of this branch. Okay. Now that we have understood how the MCTS works, let's see how the value function is being updated for a node. So the value function is just nothing but a combination, convex combination, because lambda is probably between 0 and 1, I'm not sure. Anyway, so this is a combination of the value that the current large language model thinks and the reward that you actually get by executing the function, right? And where lambda is balancing which one you want to pick. Okay, so once you have evaluated it, you have gotten a reward, you have decided right, you have decided what is the expected value, you will back up these values. How do you back up? You back up through the path from the root to the, all the nodes in the path from root to the leaf node that you just executed, right? And how do you update? You will update the number of times each action was visited, and then you will also update the q value, which is simply nothing but the average of the values you have seen so far for that particular path, right? Okay. uh, in this case, what they do is that how do you get the value, how do you get this particular value, how does large language model predict this, right? So that's an open question we have not addressed so far, because large language model gives you a probability distribution over the next set of tokens. It does not tell you what is the value of the partially generated solution so far. So what they do is that, let's say you pick GPT-4 for this. So they have GPT-4 and they predict. GPT-4 gives you the distribution over the all the possible vocabulary, right? This is the vocabulary. So what they do is they pass it through another linear layer. This linear layer gives you the value of the partially generated solution so far. Okay, this linear layer is being trained in an end-to-end using the code or using the iteration generated using the Monte Carlo Tree Search. So that's what the section 3.2 talks about, that is they are doing an iterative training. Let's go to the algorithm, how they do the iterative training. So what they do is that from a tree TK that you have generated so far using the Monte Carlo tree that you have seen so far, right, in the kth round of Monte Carlo, right, you simply sample positive and negative solutions that you have seen so far, right? You might have seen solutions to the code which did not give you the desired result, and some sequence of codes which gave you the desired results. And simply what you do is that you create a loss function based on two terms, right? Here we have two terms, first term and the second term. Let's go through them one by one. The first term says that you simply try to maximize the log likelihood of the positive outcome. That means you would like to maximize the likelihood of the code that led you to a positive result, right? In the second term, they simply say that for positive as well as for negatives, you simply take a loss function on the predicted value, that means v5, and the actual value that was seen, and you try to reduce their values, right? So this part of the loss function is training the language model directly, whereas the second part, this particular part, is trying to train the value function. Okay, so that's what they are doing in the training method. Okay, so now this is for the training. The third step or the final step would be how do you go about doing the inference at the test time or in the production, right? For this, let's go to the algorithm that we have seen, that we are just about to see. Okay, in this case I'll use a black pen here. In this case, what they do is that how do you infer using MCTS? So what they do is that first you build a tree T using MCTS that we have seen, right? Then once you have this, what you will do is that you will walk through the tree one by one, right, and pick the actions that led you to the best results, the path that led you to the best results, and you pick the corresponding action, execute it. That's it, right? That's what they have done. For you first build the tree, then you initialize a priority queue C, that means what is the current set of states to be visited. Then for t less than small t less than greater t, right, for a time period, that means, and you have not encountered a terminal state, you initialize the priority queue, that means a queue over the next possible tokens for each st in C, that means for all the tokens that you want to expand in st, right, that means s naught in our case, for each of the like children or next possible tokens as per the MCTS tree, right, you simply concatenate the next token, add it to CT plus 1, that means it is the possible action that you can take, and at the end you take the top B1 of these, where B1 is set to the value 1. So essentially, let me walk you through this, that once you have generated this particular tree, right, you may have other actions also. You simply pick the best one that you among these, And how do you take the best one among these? You simply check argmax over the q values. The whichever of these action leads to better results, you simply pick that. That's what this inference algorithm is talking about in its fundamental nature, right? Now let me just clean this up a bit. Once you have that, once you have done this, but this you can see that this might be very expensive, right? You have to traverse each and every node in the tree and go on about it. So how do you change that? What you do is that you simply use a beam search on top of it, right? That means you do not visit each node of the tree, you simply do a beam search where you keep the top k of these. And here, if you notice in the MCTS algorithm, that means the first algorithm, they use the actual value, q value of the that we got from the MCTS. But in this case, to avoid that, what we can do is that we can use a large language model. We have already trained a value function. So whatever node you visit, you can simply ask the large language model to predict the value, and based on that you can select. And this is what the difference between these two is. And the second algorithm is known as step level beam search, right? So this is the algorithm that they have done, and they show in their experiments that this leads to better results. I'm not going to go through the experiments because I'm more focused on the ideas that they have used. Otherwise the video will get very long. So that's all for today. Let me summarize it a bit. What they do is that they use a Monte Carlo Tree Search algorithm to allow the large language model to generate a piece of code of what it thinks about, right? Then that piece of code is executed using a Python interpreter. The result is returned, and that result is used to create and expand the Monte Carlo tree. Once the Monte Carlo tree is expanded, they simply take the argmax over the best action that you can take. But this is infeasible in practice for production. So they use a beam search on top of it. So that's all what is there to this particular paper. Thanks.